Hello. In this video, we are going to learn about integral test to check the convergence or divergence of a series. As the name suggests, it is using integral. If you remember, we did improper integrals in chapter 7. That is what we've been using here. Suppose that f is a continuous positive and decreasing function on 1 to infinity. So first of all, to use this test, you need to have three conditions satisfy the function. Okay. So your f has to be continuous. That is the first condition. It has to be positive. That's the second condition. And it has to be decreasing. Okay. So this is one clue that this test applies when we have positive terms series. Okay. Suppose we have a series n is from 1 to infinity. That is why all this has to be true on 1 to infinity, because our series starts from 1. We are only worried about 1 onwards. Okay. So we take off an and write it as f of n, and from there we get f of x. That is our function which we use. We say, suppose f is continuous, positive and decreasing on the given interval. If that is true, the function which we are using is same as an for n more than or equal to 1. Then the series converges if and only if this integral converge. And what is this integral? This is the integral, like an improper integral, right? We have already worked on how to check integrals converge or diverge. So to check if the series converge, I can just check the integral converges or diverges. If integral converges, the original series converges. If the integral diverges, the original series diverges. So they both converge or diverge at the same time, provided what when we can do use this if all these three conditions are satisfied: continuous, positive and decreasing. So before even you start applying integral test, you need to check for continuity, positive and decreasing function. So we have this series here. We need to check if it is convergence or divergence. Okay. We notice that series has positive terms. There is no alternating series. There is no negative sign. Okay. That's first observation. So looking at the an is n square by n cube plus 1. So corresponding function which we are going to use is f of x is x square by x cube plus 1. So you just need to replace n by x here. Okay. Now we need to check three conditions. Remember, continuity, positive and decreasing from 1 to infinity. We talk about 1 to infinity because series only is from 1 to infinity. Now, if I put any number from 1 onwards, this x is positive, so the whole thing will be positive. X squared is positive, so the whole thing is positive. F is positive for x more than 1 or equal to 1. So true. One condition done. Okay. Continuity. If for this you can also just check the graph of the function. Here I have x square divided by x cube plus 1. This is the function, and we are only worried about from 1 onwards. Okay, so you guys notice after 1 the function is a decreasing function. Okay, continuous, not breaking anywhere, it's a decreasing function. Coming back, so we can say f is continuous also. Looking at the graph, continuity is checked, the positive is checked. For decreasing, the graph is good enough. You can also find the function's derivative. You guys know how to find the derivative of this? The derivative of this is x cubed plus 1 whole square. I'm applying quotient rule. Derivative of x square is 2x times x cubed plus 1 as is minus x square as is. Derivative of x cubed plus 1 is 3x square. So what do we have? 2x4 plus 2x minus 3x4 by x cubed plus 1 whole square. If you guys notice, this whole thing is going to come to be negative x4 plus 2x by x cubed plus 1 whole square. Observe that the denominator is always positive, right? And if x is more than or equal to 1, this x4 is going to be larger than 2. So this whole thing, I know at 1 it's not negative, but generally after 1 it's always going to be a negative number. If f prime x is a negative number, in general, even if it's not at 1, we can say 2 onwards, f is a decreasing function. Okay, so what are we saying here? We are saying f is a continuous function because we saw the graph. It's a positive function because whenever we put positive numbers in this, it's always going to stay positive. And it's decreasing because the derivative is negative. So you need to show me that these three conditions are checked. That means the series behaves similar to the integral. Integral is 1 to infinity f of x dx. Now, we important point, we notice that f is decreasing after x is more than or equal to 2. So we need to do the integral from 2, okay? But just one extra term is not going to change. They both still are converging or diverging at the same way because of the integral test, okay? So we need to find this integral. This need to be done using improper integral. So in place of infinity, we're going to put some b here and we're going to say b is approaching to infinity. The function is x squared by x cubed plus 1 dx. How are we going to do this integral here? If you notice, derivative of the denominator is kind of sitting above. So I'm going to use my, use substitution. So u is equal to x cubed plus 1 du would be what? 3x square dx. So x squared dx is du by 3. That means integral x squared by x cubed plus 1 dx can be written as what? 1 by 3, 1 by u du. Because this is u, x squared dx becomes du by 3, which is 1 by 3 natural log of u. 1 by 3 natural log of x cubed plus 1. I don't really need to put bar because this is a positive number for 2 onwards, okay? So that means what I'm saying here is my limit b approaches to infinity 1 by 3 log x cubed plus 1 from 2 to b. Okay, what do we have? We put the upper limit minus the lower limit, 1/3. Limit b approaches to infinity log b cubed plus 1 minus log, when you put 2 in there, 2 cubed plus 1 is 9. Now notice when b is approaching to infinity, b cubed plus 1 will approach to infinity. Log of infinity is also, log of infinity is infinity because you remember log's graph goes like that, right? So it goes to infinity as x approaches to infinity. So therefore this whole thing is infinity. If this whole thing is infinity, we can say this integral diverges. If this diverges, our integral test says the series also diverges. So the answer for this series would be diverging series. This is diverging using integral test.